All right, so we're going to be doing addition and subtraction with radicals. And anytime you do anything where you're adding, one of the things that we have to focus on is the fact that we need something that's similar to be able to add. So for example, you add numbers together. You can add variables together as long as the variables are the exact same variable type raised to the same power. So it's no different than if I were to give you an expression like 3x plus 7x, you know exactly what to do. You know that you're focusing mainly on the 3 being added with the 7, and that your variable, your x, is just going to remain as it is. It's unchanged. So really we get what? 10x, right? It doesn't become 10x squared. It still remains 10, and then the x stays exactly as it is. The reason that we can combine those numbers together is because we have that like term. They both are in terms of x's, meaning that we have 3 x's that we're now combining or adding together with 7 x's. That's different than multiplication. Multiplication is how we get those exponents. Okay, if I was multiplying 3x times 7x, that's then when I would get an x squared, 21x squared. It's the same thing with radicals. But in this case, you're having to combine like radicals. Okay, you add fractions with like denominators. You add expressions with like terms. You add radicals that are like radicals. And to be a like radical, it means you have to have a common radicand. Who remembers what do I mean when I say a radicand? Where's the radicand located? Inside. It's inside of that square root or that root. So it has to have a common radicand. Which means that the number that is inside the root has to be the same, or the value. Okay, it doesn't necessarily always mean it's a number because there could be a variable that's inside as well. It just means that the radical itself, what's inside of the radical or inside of the square root, has to be identical in order for you to combine. So the number or value inside the root. That's what we're focusing on when we say radicand. So for example, if I give you 2 square roots of 5 plus 4 square roots of 5, again, the radical square root of 5, those are like radicals. They are the same. So we're going to focus on just adding 2 and 4 together to get 6, and then it's square root of 5. Just like when we add variables together, the variable remains unchanged. It's only the coefficients that are being affected. Same thing for here. The radical remains unchanged. It's just the coefficient to the radical that's being combined together. So let's take a look at a couple problems. So we have 3 square root of 7 plus 8 square roots of 7. I want you to try that on your own. I'm going to put a couple of them up here. All right, who can tell me what they got for problem number 1? Emiliano?
11.
Good. 11 square root of 7. Again, the radical is the same. They both have a radical of square root of 7. So that means you're just going to focus on combining the 3 plus the 8. And 3 plus 8 is going to give you 11, so you get 11 square roots of 7. Okay, what about for problem number 2? Go ahead, Brett.
9.
Nope. Jimmy Ho? 8 square root of y. So remember, if you do like 5x minus x, the x's don't disappear, right? 5x minus x, that minus x is really what coefficient? A 1. So it's really 5x minus 1x. It's the same thing here. It's not just 9y minus, or 9 square root of y minus square root of y. It's 9 square root of y minus 1 square root of y. It has a coefficient of a 1. You just don't have to put it. So because they are the same radical, you're focusing on just subtracting 9 minus the 1, and that gives you 8 and then square root of y. What about number 3? Somebody else. Jimmy Lynn? Nope. Antonio?
8 square root of 11.
Nope. Solomon? Nope. Jimmy Ho? Are they the same?
No.
If I asked you, could you do 4x minus 3y, could you? Why not? Because it's not like terms. Are those like? No. So can we do that? No. So your final answer is 12 square root of 2 minus 4 square root of 11. That's your final answer. That was a trick because of the fact that they are different radicals, right? Or different radicands, we'll put it that way. Different radicands. So you cannot subtract. So your final answer is going to be 12 square root of 2 minus 4 square root of 11. That is it. That's your final answer. That's as simplified as that will get. So be careful about that then when you get to problem 4. With problem 4, is everything a like radicand? No. Which one's the one that's not the same? 6 square root of 2x. 6 square root of 2x is not the same as the other radicals. The other radicals have similar radicands of a square root of 3x. So those are the only ones that you could actually focus on combining. These are the like radicals. So if I were to go ahead and rewrite it as negative 8 square root of 3x plus 10 square root of 3x, those I can go ahead and combine, but this plus 6 square root of 2x cannot, so I'm going to go ahead and put it off to the side. And what do we get when we combine a negative 8 square root of 3x and a positive 10 square root of 3x? 2. So we get 2 and then the square root of 3x plus 6 square root of 2x. And that's your final answer. Any questions so far? You have to make sure that you only combine if they are like radicands. Now sometimes they might look like they're not like radicands, but in fact that they are. So if I have the square root of 12 plus the square root of 27, right now do they look like they're like radicals? No, but they are. Why are they? What can I do, Solomon? They both have a what in them? It's good thinking, but that's not the right process. Why are they alike, Saja? They're both divisible by 3, sure, but that's still not why. When you simplify them, when you factor them apart, they both wind up having a non-perfect radical that's the same. They both have that non-perfect radical, which is the 3. If you divide them both by 3, then you're leaving them both with perfect squares left over, right? 12 divided by 3 gives you 4. 4 is a perfect square. 27 divided by 3 gives you 9. 9 is a perfect square. So you're left remaining with that non-perfect square of a 3. So again, sometimes you might have to factor them down, simplify them out to see whether they are able to be combined. So if I break the 12 up to square root of 4 and square root of 3, again, the square root of 4 is a perfect square. It comes out to being 2 square roots of 3. And then when I factor out the 27, it becomes square root of 9 and square root of 3. Again, 9 is a perfect square. That gives us 3 square roots of 3. And then our operation is still addition. Now we do have identical radicands. Therefore, we can go ahead and combine the 2 plus the 3 to get 5 square roots of 3 for your final answer. Try number 6 on your own. So how can you factor 8? Break it out to 4 and a 2. Then take the square root of that 4. All right, who can tell me what they got for problem 6? Jimmy? Very good. 6 square root of 2 plus 3 square root of 5. Even when you factor this down, it still didn't factor down to things that you could combine together, but at least you're still simplifying it. You never want to leave it in this format because it's not simplified. You always need to simplify. It's no different than if you had fractions. You have to simplify the fractions. Same thing here. You have to simplify your radicals always. Then you check to see if they can be combined together or not, which in this case they can't. Factors for 8. 2 and 4. So we have square root of 4, square root of 2. We still have that 3 that's going to run in the front. And what's the square root of 4? 2. So we now have 3 times 2, square root of 2. And what's 3 times 2? 6. So we get 6 square roots of 2. Then we move on over to the 45. Factors for 45? 9 and 5. So square root of 9, square root of 5. 9 is the perfect square. What's the square root of 9? 3. So we get 3 square roots of 5. Again, these are not like radicals, so you cannot combine them together. Therefore, this would be your final answer. Go ahead and switch on over to the next page, please. Try that one. So if I switch the page, you switch the page. But if you want to do like, this page is page 1, and then the back of it is page 2, and the next page is page 3, and the back is page 4, you can do that. I don't do it just because it bleeds through. Not if you have a 3 subject. If you have a 3 subject, you shouldn't. All right. Somebody who hasn't answered. Musa. Ooh, so close. So close. Ashton? No. Antonio? No. Sanaya? 3 square roots of 2x. 3 square roots of 2x. So let's take a look. Can we factor 2? No, can't factor the 2. Can we factor 8? Yeah, we can factor the 8, right? So we know that this is going to become a square root of 4 and a square root of 2. Where's the x going to go? With the 4 or the 2? The 2, because it's not perfect, right? So we're going to leave it with the non-perfect. What about 32? Can we factor 32? Yes, 16 and 2, right? And again, the x will go with that 2 because the x is not perfect. This square root of 2x cannot be factored out, so it's just going to stay square root of 2x. So we have this. Now, square root of 4 is perfect. Square root of 16 is perfect. We don't have a coefficient in front of the 2x, but what is there? A 1. We know that there happens to be a 1 in front of this 2x. Minus, what's the square root of 4? 2. So we have 2 square root of 2x. Plus, what's the square root of 16? 4. So we have 4 square roots of 2x. So now, every single one of these is a like term. That's a like term, like term, like term. They're all square root of 2x. Because they are all like terms, we're going to focus on 1 minus 2 plus 4. 1 minus 2 is going to give you a negative 1. Negative 1 plus 4 is going to give you a positive 3. So you have 3 square roots of 2x. Okay, let's try another. Do you have a question? I'm going to try to get people who haven't answered. But thank you so much. You've been volunteering a lot. Not the outside value, no. But you do utilize it that once you factor and simplify that radical, then you use the outside value to multiply whatever perfect square you factored. All right. So who thinks that they've got this? Solomon, what do you think? Not 11 square root of 3xy, but close enough. Richard, 13 square root of 3xy. 13 square roots of 3xy. So let's take a look. Okay, we've got the 4 square root of 12xy. 12 can be factored. It can be broken down to a perfect square. So we know we've got the 4 still remaining. Then we've got that square root of 12 can be broken down as a square root of 4 and a square root of 3. We're going to let the x and the y remain with the non-perfect square root. Plus 75 can be broken down into the square root of 25 and then square root of 3, and the xy will remain with it. Now square root of 4 is going to give me a 2, so I now have 4 times 2 square root of 3xy plus the square root of 25 is a perfect square, so that's a 5 square root of 3xy. Now 4 times 2 is going to give me 8. So I have 8 square roots of 3xy plus 5 square roots of 3xy. And because they are like radicans on the inside, we can go ahead and combine 8 plus the 5. And 8 plus 5 is going to give us 13. So we get 13 square roots of 3xy. We'll try one more. All right. Jane, what did you get? Not 10 square root of 3, right? Notice that this is a minus, so that makes it a negative, and this is a plus. So figure that out. Fix that. It wouldn't be 10 because it's really like a negative plus a positive. So what would you really get? Go back to your last step when you combine those at the end. Emiliano, you want to help her out? Negative 2 square root of 3y. Because you got that negative 6 when you simplified it, negative 6 square root of 3y, and then a positive 4 square root of 3y. Negative 6 and a positive 4 will give you a negative 2. So let's go ahead and take a look at that. Again, we have that 9. It's already outside of the root. We can break 75 up into the square root of 25 and the square root of 3. Then we have a minus 2. Break the 27 up into the square root of 9 and then the square root of 3y. Notice that the square root of 3 and the square root of 3y are not the same. One of them has a variable and one of them doesn't. Therefore, you cannot combine those together. Then you've got a plus. There's not a coefficient written, but I'm going to go ahead and write a 1 just in case. And then the 48 can be broken up into the square root of 16 and the square root of 3y. Okay, our perfect squares are 25, 9, and 16. That leaves us with 9 times 5 square root of 3 minus 2 times 3 square root of 3y plus a 1 times a 4 square root of 3y. Okay, so 9 times the 5 is going to give you 45 square roots of 3. Negative 2 times the 6 is going to, or times the 3 is going to give you negative 6 square root of 3y. And then a positive 1 times 4 is going to give you a 4 square root of 3y. Again, the ones that are like terms are going to be that square root of 3y here. Those are the like radicals. Therefore, we can focus on a negative 6. That minus sign in front acts as a negative. Don't forget that. And a positive 4. That 45 square root of 3 is not going to change. It's going to stay 45 square root of 3. But when you take a negative 6 and add it with 4, you're going to get a negative 2 and then square root of 3y. And that's your final answer. Are there any questions about this? Okay, on page 20 is where your homework assignment is going to go. You'll glue it in.